Now we have our last lecture with Professor Carlos Varea about generalized complex structures on flag manifolds. So it's up to you.
Thank you, Jordan. I would like to thank again the organizers for the invitation to present this mini course. So today is the third day, last day of our mini course. So far, we saw in the first day the preliminary concepts, some concepts on generalized complex geometry, the definition of flag manifolds that we are using here. On the second day, we saw a lot of computations, but we described all generalized complex structures on flag manifold, well, at least the almost ones, without worry about the integrability. So today, the idea is to talk about these integrability conditions for these structures. Okay? So just remembering that when we have an invariant generalized complex structure on a flag manifold, we can decompose this flag manifold in block, this structure in blocks in the diagonal, where each of these blocks, each of these j alpha k, will be an invariant generalized complex structure on the root space U alpha. So it's a four-dimensional matrix, which we saw on the last lecture that they can assume two forms, which we call complex type, the first one, because it comes from a complex structure. And the second we called non-complex type, where we have this additional condition here. So to construct these invariant almost complex structures on flag manifold, we basically combine these two types in the diagonal, like here. We can put complex type, non-complex type, and so on, as much blocks as positive roots in the algebra. But when we talk about, when we have the integrability conditions, we get something more rigid. So we don't have this freedom to combine any type in the diagonal. So let's see how it works here. So remember that in the first lecture, we saw that the integrability for generalized complex structures depend on the Coulomb bracket, which is defined by this expression here, where on the right-hand side, we have the Lie bracket for vector fields, and here we have the Lie derivative. So the idea is to rewrite this Coulomb bracket in terms of the elements of the Lie algebra and the dual of the Lie algebra that we are working here, to get a more easy expression for this bracket. Okay? But it's important to notice that we are identifying the tangent space with the cotangent space at the origin by means of the constant Kirillov-Soryov form. This omega 0 will be the KKS symplectic form. Okay? When we restrict the constant Kirillov-Soryov symplectic form. So when we restrict at the origin, the expression for the symplectic form is just the killing form of the bracket of x and y, where this tilde represents the fundamental vector field associated to x. Okay? So this is the identification that we are using to identify the tangent space with the cotangent space. Okay, so the elements in the dual will be denoted by x star, which is a constant times the KKS symplectic form at the origin restricted to dx. Okay, we are going to call this constant of k alpha, and the idea is this that I said, that is use this identification to rewrite the Coulomb bracket. Okay, so the Coulomb bracket is given by this expression. So the idea is to see what is the expression for this guy here first, and then we are going to see what's the expression for the other guy. So let's consider an x in the tangent space at the origin and a y on u alpha. Okay, I'm going to consider an element on u alpha. We could consider an element on M, but we can use the linearity here. So it's to get easier computations, we are going to use only on u alpha. Okay. So let's describe this guy here in terms of this identification here. Okay, so using the Cartan magic formula, we know that the derivative of these guys can be rewritten of this way. But the second term that appears here, we are differentiate is the differential of an element which is given in terms of the KK asymptotic form, which is actually the differential of the high function. Okay, so this part here will be 0. So the Lie derivative of this guy will be just the differential of this guy here. Okay, so these two guys here can be rewritten using this expression. So let's see what is the expression of this guy, which is quite similar to the guy that is appearing here in terms of our identification. So we will apply it on an element Z. So this just using the definition of this guy here, which is a constant K alpha of the KK asymptotic form on these guys here. So when we differentiate it on the direction of Z, we obtain this expression here. And using the definition of the constant the KK asymptotic form at the origin, we obtain this expression here. There is another guy. So we obtain just this expression. And by using the Jacobi identity, we can reduce the expression for this. So the differential of this guy here is just a constant of this guy applying on someone of the bracket of x, y, and x. So this is the expression for this guy here. So the idea is just replace all these identities on the expression of the Coulomb bracket. So this is the expression of the Coulomb bracket applied on this element x plus y star and z plus w star. So observe that the Lie derivative is just given by this expression here that we obtained first. And this guy here is exactly what appears here, and this guy here is exactly what will appear here. So we can simplify the expression. So this is the expression of the Coulomb bracket. But we have this other identification for the differential of this guy, so we can replace this expression here. So in terms of the elements of the Lie algebra in its dual, the Coulomb bracket is given by this formula in here, okay, where I am taking y and w elements on u alpha and u beta star. Again, you could take elements on the tangent space, and then you can use the linearity to separate each part. Okay, so there is no loss of generality of taking elements here. Okay, so this is the expression for the Coulomb bracket. But remember, when I introduced the notion of integrability of generalized complex structures, we presented also another way to look the integrability, which was by means of the Nyhan-House operator, which is given by this expression here, where we have here on the right-hand side the bilinear form on the tangent space plus the cotangent space, and here we have the Courant bracket. And we have the cyclic permutations of these guys. Okay, so using this expression of the Courant bracket, the idea is to obtain a better expression for this Nyhan-House operator. Better because it's in our language, in the language of the Lie algebra and its dual. Okay, so it's a big expression, so we are going to compute each part separately. So first this, and then this, and this, which is quite similar. So consider elements A, B, and C, each one on the space, the word space plus its dual. So A on U alpha plus U alpha star, B on U beta plus U beta star, and C on U gamma star. So the first part of on the right-hand side of the Nyhan-House operator is the bilinear form of the bracket of AB with C, which is this part here. Okay, so we have this expression here. So using the expression for the Courant bracket that we obtained, we get this expression here. Okay, because A is on the root alpha and B is associated to the root beta. So this is what we obtain here. And then we apply the definition of the bilinear form for the tangent plus the cotangent space that we saw in the beginning of the first lecture, which is half of the dual part here, okay, is half of the dual part here applied on the vectorial part here, plus the dual part here applied on the vector part here. Okay, this is the definition of this bilinear form. So when we do this, we obtain this expression for this first part, for this first guy here. Okay, so this is the expression for this first part. And if we replace these identifications on the other two parts, so for the cyclic permutations of these guys, we obtain these other expressions. And then the Nyhan-House operator, remember, it is 1/3 times the cyclic permutation of this guy. So it's basically sum this expression here plus it's this expression here and here. So when we do this, we can use the linearity, use Jacobi identity, and we are going to obtain this expression here. Today, I'm not going to do these computations because it's a little technical, and I think I already did a lot of computation with you last lecture. So when we put these three parts and use linearity and Jacobi identity and some properties, we obtain this expression for the Nyhan-House operator. So it still is a long expression, but it's in terms of elements of the Lie algebra. Okay, so it's a better expression for us. It's in our language. So the idea to analyze the integrability by means of the Nyhan-House operator is to restrict this operator to the eigenspace of the generalized complex structure. But before I start to do the computations with this, to restrict to the eigenspace, there is an important remark to do. If you are familiar if you have knowledge of the study of integrability for complex structure, not generalized complex structure, on flag manifolds, you know that the integrability depends on triple of roots alpha, beta, and gamma, satisfying the condition that the sum of them are zero. Okay, and for us, for the generalized complex structures, we obtained a similar condition, and the integrability will depend on triple of roots satisfying this condition here, that triple of roots of the type alpha, beta, and alpha plus beta. Okay, let's see why this happened. So, for example, if we consider the Nine-house operator restricted to just one root, for example, alpha. So in U alpha plus U alpha star, you have the elements A alpha, S alpha, A alpha star, S alpha star. So let's see what happened with the Nine-house operator restricted to these guys here. So just using our expression for the Nine-house operator, we will obtain this, just this guy here. So using the property of the Lie bracket between these elements A alpha and S alpha, we have that this is 2I times the H alpha. And again, using the properties of the Lie bracket, we obtain this expression here. But S alpha is orthogonal with respect to 8, okay? So it will be 0. And the same will happen if you run over all elements of U alpha plus U alpha star. So when we restrict the Nine-house operator to one root, we obtain immediately that it's 0. And the same will happen if we restrict to only two roots. For example, if you change here this A alpha star for some element associated to the root beta. The same will happen. You will obtain some element here which is orthogonal to alpha. Okay? So when we restrict to only two roots, again we obtain that the Nine-house operator is immediately 0. The only possibility is when we have three roots of the type alpha, beta, and alpha plus beta. Because again, if you have three roots, alpha, beta, and gamma is different from alpha plus beta, plus or minus, you will obtain some guy orthogonal to alpha, so it will be 0 immediately. So the integrability will depend on triple of roots of the type alpha, beta, and alpha plus beta. Okay? So let's do an example to see what happened with a triple of roots alpha, beta, and alpha plus beta. Okay? So, for example, this guy here, A alpha, S beta, and A alpha plus beta star. Applying the definition of the Nine-house operator, our expression gives us this. Then the Lie bracket between these two elements is given by this expression here. But you can use the bilinearity of the Lie bracket, and A alpha plus beta with S alpha minus beta will be 0, so it will remain just this guy here. And then using the Lie bracket, again, the properties of this guy here, remember that the bracket between A alpha and S alpha is given by this expression here. So here appear again A alpha plus beta, S alpha plus beta. So it will appear the killing form of H with H alpha plus beta, and it's non-zero. So this expression for the Nine-house operator will be non-zero. So the idea is to compute all the possibilities between the basic elements for triple of roots alpha, beta, and alpha plus beta. So the space U alpha and U alpha star will be generated for elements for this guy here, these guys here. Okay, these 4 elements for each root. So the idea, what I did was to compute the Nine-house operator with all combinations for triple of roots. So put alpha here, beta here, and alpha plus beta, and run over all possible combinations of the basic elements. And after do after all these computations, we obtain that the only cases where the 9-house operator is non-zero are these 12 guys here. Okay? If you pay attention on this guy, we always have 2 A's and 1 S, or 3 S elements. 2 vectorial and 1 dual. Always this is happen. 2 A and 1 S, or 3 S. Always 2 vectorial parts and 1 dual part. Okay? It's just linear algebra after you have the expression for the 9-house operator. Okay, so it's just do the computations. So these are the possible non-zero 9-house operator. Okay, so as I said, the integrability depends on the eigenspace of the generalized complex structure. So each block of our generalized complex structure is either of complex type or non-complex type. Okay, so when we consider the complex type and you compute the eigenspace, just the normal, just computations, the eigenspace as we see in linear algebra. So we obtain this space here. Okay, plus or minus depend on the sign of the complex type, the structure of complex type. And when we consider the non-complex type, we obtain this expression for the eigenspace. Okay, so this is the expression for the eigenspace of the complex type or the non-complex type. So what next? So now we need to analyze all the possibility combinations for triple of roots of the type alpha, beta, and alpha plus beta. So consider a triple of roots, alpha, beta, and alpha plus beta. And then we are going to consider all possibilities to the eigenspace associated to this triple of roots, which is L alpha, L beta, and L alpha, that I called here L alpha, beta, and L alpha plus beta. An important remark here is that the sign of the complex structure, the structure of complex type, interfere directly on the integrability. Now, I will show an example later, but so we have a triple of subspace of eigenspace, and we can have complex type or non-complex type. But the complex type here has the sign plus or minus, so we will have 3 types. Okay, complex type positive, complex type negative, and non-complex type. And what I did was to compute all possible combinations. So we have 3 types for L alpha, 3 for L beta, and 3 for L alpha plus beta. So we have 27 combinations of eigenspace to restrict our 9-house operator. Okay, so let's do an example to see how it works. Okay, so let us suppose that we have a generalized complex structure, and for a triple of roots, we have the following associated eigenspace. L alpha is of complex type with positive sign, so J alpha is that matrix like this. J beta is the same, and J alpha plus beta is of non-complex type. Okay, so to analyze the idea is just to analyze the 9-house operator restricted to the eigenspace of this guy. Okay, so the thing is, if you find that the 9-house operator is non-zero for some combination, it will not be integrable. If it's integrable, then you need to show that it's 0 for every possible combinations. Okay. In this case, when we consider these guys here, so one element of L alpha, one element of L beta, and one of L alpha plus beta. So we can use the linearity, the multilinearity of the Nyhan-House operator, and we are going to obtain that remains only these guys here. Because remember, the Nyhan-House operator is always 0, except when we have 2 A's and 1 S, or 3S, always 2 vectorial parts and 1 dual. So here we have, for example, A alpha plus beta, A alpha star, A alpha plus beta. It's 0. A alpha plus beta star, A alpha, A beta star, A alpha plus beta star. We have 2 dual parts, so it's 0. And we start to do all possible combinations just using the distributive, using the linearity to distribute these elements. So we obtain that only these 2 guys here will remain. And these 2 guys here, remember the case where the Nyhan-House operator is non-zero, these guys are equal. So we have 2 times this guy, which is non-zero. So if this guy is non-zero, we have that the complex structure where we have a triple of roots alpha, beta, and alpha plus beta appearing a triple of eigenspace space of this type here, it will not be integrable. Okay? When I said that the sign interfered directly on the integrability, is one example here is the following one. If we consider J beta equals minus J alpha, so it's minus this expression here, so it will appear a plus here, this case will be integrable. Okay, so this is why you need to consider positive and negative separatedly. Okay, so okay, this is just to do the computation, and after you do the 27 possible cases, you can conclude that this table here shows us the possible combinations where we have the Nyhan-House operator 0 for triple of roots of the type alpha, beta, and alpha plus beta. And here we have the signs associated to the complex structure. Okay, so plus, 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 or minus, 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 and so on. And in the last row, where appears the only non-complex type structures, we have this additional algebraic condition to be satisfied. Okay, so it will be integrable. It satisfies also this linear system here. Okay, so at this point, we already have it all the conditions to integrability, but it's quite complicated because, okay, you have a generalized complex structure. Then to analyze integrability, you need to consider all possible combinations or roots of the type alpha, beta, and alpha plus beta. And it can be a lot of work to do, because if you have groups with dimension 2, depending on the dimension, you have a lot of roots, so it's a lot of work to analyze all roots. So I remember when I did all these computations, I think I got to, I had a meeting with Professor Samartin, and I went to, I got with, I don't know, 40, maybe 50 pages of computations, and I said, there it's all possible. All possibilities of integrability is here. And he said, okay, so let's look some pattern, let's look some kind of regularity and try to write these guys on propositions, on theorems. So we start to work on this, and we got this result here, which is a key result for the following theorems that I'm going to show. So this proposition says the following. When we have an invariant generalized complex structure, which is integrable, then the set of roots such that when we have, for example, the set of roots such that J alpha, if J alpha is of complex type, then J alpha has positive sign. And the roots such that if J alpha is of non-complex type, then the element X alpha that appears on the matrix of the non-complex type is positive. So this set is a choice of positive roots for some lexicographic order. This is an important result for two reasons. First, because it's the key for the proof of the following two theorems. And also, let me write here, when we studied the invariant invariant complex structure, it goes back to Borel. I think Claudio Gorodsky made a comment on his mini-course on the first day. I think it's on 1953. He has a series of works where he proved that actually any invariant almost complex structure on a flag manifold, if we consider here his J an invariant almost complex structure, J can be described in terms of the signs. J will be described is always like this. So if we consider, I don't know, let me write like this. Let's put this epsilon alpha, where epsilon alpha is plus or minus 1. In some papers, you can find actually J is described by the signs, okay, where epsilon alpha is plus or minus 1. And Borel proved that actually the set of the roots where the sign is positive, this is a choice of positive roots. If we have J integrable, then this set is a choice of positive roots in some lexicographic order. So this result also generalize this result from Borel, because when we have a generalized complex structure that comes from a complex structure, then the second line doesn't exist. So we have only the first line, which we are choosing exactly the complex structure with positive sign. Okay, so this is important in this sense because it generalizes a result from Borel. Okay, so using this proposition, we can prove the following theorem. So when we have J an integrable invariant generalized complex structure, then there exists a simple root system, sigma, and a subset of sigma, such that J alpha is of non-complex type for the roots inside the generated by theta. This notation here means the generated. It means that if alpha and beta are on theta, then alpha plus beta will be in here. Okay? And if J alpha is of complex type, so there existed this simple root system and a subset said that for the roots inside the generated by theta, J alpha is of non-complex type, and outside of this guy, it's of complex type. Okay, if we consider only positive roots, so we have positive sign for X alpha here and J alpha with positive sign here. Okay, and reciprocally, when we have a simple root system and a subset of it, we can construct an integrable invariant generalized complex structure satisfying these two conditions, so that J alpha is of non-complex type for the roots inside the generated by theta and of complex type outside there. So these two theorems, they basically they contain all the information that had in this table here. So we were able to put this table into theorems that are these two guys here. Okay, so this is where I wanted to this is what I wanted to show to you. But before I finish, let me do just 2 comments here. In the second lecture, Professor Jorge Lauren did a question, was about the simplex type structures. And in our joint work with Elizabeth Gasparin and Fabricio Valencia, we proved that we classified the invariant generalized complex structures on maximum flag manifolds up to B transformations. And one of the results is that the simplex, the non-complex type is actually a B transformation of a simplex type. So basically, up to B transformations, what we have are complex type and simplex type. In this same work, we also computed some moduli space, and we also classified the generalized scalar structures on maximal flag manifolds. Okay, and another comment, important comment, is here we talk only about partial flag, only maximal flag manifolds. Yeah, I have also I have a work, a paper on partial flag manifold. Is also part of my PhD thesis. The question is, the isotropy representation on partial flag manifold is a little more delicate. We need to be careful when we are working there, yeah. Because when we are on maximal flag manifold, the irreducible components of the isotropy representation are the root space. So each root space is a component of the isotropy representation. But on partial flag manifold, we do not have this regularity. I think Lucas Seco, Professor Lucas, did a comment on his talk that we have the classification for, I don't know, I think it's up to 5 isotropy summands. And in my work, I classificate all possible invariant generalized complex structures on partial flag manifolds with 2, 3, and 4 isotropy summands. And for 5 isotropy summands or for n isotropy summands, you just need to do the same thing that I did on my paper. And I think I left a kind of recipe in the end of the paper, just explain how you need to do to obtain the possible generalized complex structures there. So this is why I didn't talk about partial flag manifolds in this mini course, because it's a little more technical, and I think the time wasn't enough to do this. So this is what I wanted to do. So thank you.
Thank you, Carlos. Let's thank Carlos. Now, do we have comments, questions?
Well, I just want to comment that I have here a picture of Borel Keller matrix, because it's in the transparency I presented on Monday in the Latin American conference. But well, I opened here when you start to speak it. It's like you take the vial chambers and you put signs on each vial chambers, and you change the sign when you cross a wall of the chamber. So you can do this for the integral complex structures, which are complex structures in in the Keller, taking part of the Keller method in the maximal flight manifold. Well, thank you for the course.
Questions?
So I would like also to thank Carlos. I made contact with him, so I personally thank you for these lectures. And I have a general question because I'm not so familiar yet, also with this kind of complex stuff. But there is some results of in the thesis of Ana Paula regarding a class of flag manifolds of type C that admits complex structures. So, but this is also this is only one part of this thing to get the generalized structures. You must ask to the symplectic part. There is some work in this direction. So is it possible to do something in this sense?
The thesis of Ana Paula is on real flag manifolds.
It's on real flag. I didn't say it.
Yes, here I did for complex flag. The case of real flag manifolds, I'm working with Fabricio Valencia. We described the possible generalized complex structures there, but remains two cases, C4 and D4. We are stuck in this for a while, but the problem there is that we don't have the KKS symplectic form. So this identification that I used here doesn't work there. So we need to take another path to get this identification, to describe the Coulomb bracket in the Linehouse tensor. But I'm working on this, and I wrote to Professor San Martin asking some help, and also to Viviana del Barco, because he is part of the work with them. But I need to get back to this work. It remains just two cases for the maximal flag manifolds, and the partial flag manifolds. I don't have an idea yet.
Okay. Yes, I remember in the first place, Carlos and I, we were trying to identify the tangent and cotangent spaces, bundles, using a Riemannian metric. Then the equations to compute the bracket became, well, these very difficult equations involving covariant derivatives and things like that. Then there came the idea of considering, instead of Riemannian metric, to consider the asymplectic form. Came up, and the computations were much simpler. And so this makes a lot of difference, which way you identify the tangent and cotangent bundles of a flag, a manifold.
Yeah, I remember this.
Remember
this
that
time? Yes.
Yes, the questions were very complicated. So with lots of covariant derivatives, you start to take derivatives of a Riemannian metric. It's quite hard. On the other hand, if you go to take derivatives of a symplectic form, it's much easier because you have the exterior differentiation, and this is the idea.
Okay, any other questions? I don't think that I understand very well everything, but one thing that came to my mind, it's about computations. Have you ever tried to use computer to do some computations or not? Because there are many things. You show that table, I don't know, a lot of things. Have you ever tried use roots on computer is much easier sometimes. Yeah, it depends.
I never used it on my PhD, but now working on the real flag with Fabrizio, we are trying to use, but we are not. So I don't know. I don't have experience on this, neither Fabrizio. But the problem on real flag is we have 8-dimensional matrices to do computations, and it's really, really hard. I don't know. This is why I contacted Viviana, asking her how did they do the computations for the real flags on the work with Ana Paula and Luisa Martin, because they have a lot of big matrices there. And she sent me some algorithm on Maple. I need to study this to start to try to do something on using computers, because yes, it will be easier.
Sometimes helpful.
Yeah. But no, but these computations that I showed today, it was all on hand, using my hands.
Okay. Okay, nice. Any more questions? Well, so thank you. Let's thank again, Carlos.